Okay, last session we went through Laplace transform. We found if we have a e to power of st signal, that's kind of eigenfunction for any LTI system. What does it mean? It means if I apply e to power of st to input of one LTI system, the output would be exactly like the input. The only difference is one coefficient. So if I can express any input as a function of is eigenfunction, which means if I apply this input to any LTI system, the output would be exactly like the input with one coefficient difference, which we define that coefficient as a Laplace transform. This is definition of Laplace transform of xt as xs. The Fourier transform was a simple form of Laplace transform if we consider s as only j omega, which means if we consider really part of s 0, on that case, Laplace transform can convert to Fourier transform. Here we can see Laplace transform is Fourier transform of xt e to power of minus sigma t, which means we are adding one exponential signal to the original signal, which can help us to, which gives us one degree of freedom that we can define Laplace transform for the signals that they may not have Fourier transform. If a signal has a Fourier transform, for sure we know at this end it has Laplace transform, but the reverse is not true. If it has Laplace transform, it won't necessarily have Fourier transform. And we saw it, the Laplace transform can add one degree of freedom like this to the signal, which is signals which the energy is unlimited. We can make them integrable and their energy is limited, so we can define Laplace transform for them. We saw if I have e to power of minus at ut, its Laplace transform is 1 over s plus a. Also, if I have e to power of minus at u minus t, its Laplace transform would be 1 over s plus a. What's the difference? If I give you this Laplace transform and ask you what is its Laplace inverse, how do you find? Oh, by integration. We know if I have this Laplace transform, its inverse would be one of these two. Yeah, but which one? How do you find which one is the Laplace transform? Yeah. Exactly. Depends on the region of convergence. We saw if a signal is a finite duration signal, its ROC would be entire complex plane. If signal is right-sided, its Laplace transform, again, the ROC would be right-sided. If signal in a time domain is left-sided, ROC should be left-sided. If signal is two-sided, ROC should be between two successive points. Now, For this one, if I ask you, this is my ROC, which one is Laplace inverse of this Laplace transform? The top one or the bottom one? By top one? Yes, this is right-sided. This signal is again right-sided, but this signal, that's left-sided. Yes. So the Laplace transform of the Laplace inverse of this Laplace transform is the top one, the right side. So this is an example that its time duration, the xt is, its duration is limited in time. Yeah, it's not like that. It should be. Since its duration is limited in time, we expect its ROC would be the whole f-plane except 1 over infinity. We should consider, we should investigate which one, or maybe both of them. Here, how about S0? Is it a part of ROC or not? It is. Yeah, if I replace S with 0, you can see this is 1 over A. Nothing is 1. If I replace S with infinity, it can be undefined. Yeah, depends on its real part. So for infinity, this Laplace transform is not defined. So ROC is entire complex plane except infinity. This signal is two-sided, yeah, which is in from minus infinity to infinity. So its ROC would be between two consecutive poles, yeah, as you can see here. If we write the integral and find it has two poles, and the ROC would be between these two poles. We saw for Laplace inverse, we can use this integral, which is not easy to use. So we usually use partial fraction, expansion, or other Laplace transforms that we already know, yeah, to find the Laplace inverse. For example, if we had one Laplace transform like this, we can easily separate the fractions. For A, how we find A? I omit this one, put minus 1, 1 over 1, A should be 1. For B, again, here we have s plus 2. In this case, we should omit s plus 2. For the rest, we should replace s with the root of this one, minus 2. 1 over minus 2 plus 1 is minus, and ROC is bigger than minus 1, which means for this one is right-sided, and for this one, for both ROC is right-sided. So I should use e to power of minus 80 ut for both of them. If ROC was smaller than minus 2, for both, it would be left-sided. So I have to use minus e to power of minus a u minus t. If ROC is between 2, I have 2 ports, minus 2, minus 1. ROC is between 2 ports. When I want to find the Laplace inverse of this one, ROC for this is right-sided, so I have to write it right-sided. ROC for minus 1 is left-sided, so I should write the left-sided Laplace inverse. We went through some properties of Laplace transform like linearity, time shifting, shifting in S domain. We saw this and we reached to this point. Any question up to now? It's clear. I wish. But if we do a scaling in time domain, what will happen in Laplace domain? If we make signal compact in time domain, it will spread in Laplace domain, yeah, and vice versa. This one of the most important properties. Convolution in time domain would change to multiplication in S domain. Why this is important? Yes, in all LTI systems, we have to do convolution between input and impulse response to find the output. So now I can easily find the Laplace transform and multiply them together. At the end, I need to do Laplace inverse. If I do differentiation in time domain, it can easily change to one algebraic. I just need to multiply the Laplace transform by S. What was Laplace transform of ut? 1 over S. What is relationship between impulse and step? Exact. Impulse is differentiation of step, unit step. So if I do differentiation in time domain, which means in S domain, I need to from here to here, I did differentiation. So from here to here, I need multiply it by S. You already knew that, yeah. If we do differentiation in S domain, we need to multiply signal in time domain by minus t. They're kind of dual. For example, t e to power of minus t ut. What is the Laplace transform of this signal? Yeah, we know this one. Yeah. What is Laplace transform of this one? 1 over s plus 1. Now I'm multiplying this function by t, which means I need to take a differentiation in S domain. But it should be minus t. I can multiply the two sides by minus 1. Why? Because that's linear. What is the differentiation of this one? S plus 1 to power of 2 here. 1 over s plus 1 square. Let me tell you something. How about cosine t? What is its Laplace transform? We know cosine t ut, cosine t ut. What was the Laplace transform? Exactly. How about cosine t? The difference between these two is, can I write here? This is cosine t, this is cosine t ut. If I write the definition, this is definition of Laplace transform. If really part of S would be positive, its multiplication would be in time domain, something like that. If that's negative, it would be something like that. Which means at least in one side, it's gonna go to infinity, its amplitude. So we cannot define Laplace transform for that here. We cannot find this area because it's growing. Okay, now go back here. We are looking for Laplace transform of this one.
Minus s over s squared plus
Exactly. Thank you very much. Yeah. If we multiply signal in time domain by t, we should do differentiation in S domain. If we do integration in time domain, we should multiply the Laplace transform by 1 over f. Yes. What is, yes, we saw it yesterday. Oh, for cosine. You mean e to power of minus t cosine t for t. Oh, so why, how can you? What's the Laplace transform of cosine? It's cosine t is, yes. Now, if you do time shifting, which means you just need to multiply this Laplace transform by, yes, that's done. Do you remember if I took convolution of delta t with any signal, the answer would be x xt, yeah. Delta is defined. So that's convolution, that's not multiplication. In multiplication, if you multiply xt with delta, that's sampling property, yeah. It would be x0 delta t. If we convolve xt with delta t, it would be xt. Yeah, convolution of delta with anything would be that anything. If you remember xt convolution by delta t minus t naught, the convolution would be exactly x t minus t0. I can find it another way, yeah. Xt convolved by delta t. In Laplace domain, I can change convolution to multiplication. Xt Laplace transform is xf, Laplace transform of delta 1, which is xf. Okay. Same for here, yeah. We need to multiply it by e to power of minus st0, which is gonna be multiplied by xf. So it would be xt minus t0 t9. How about ut? If we convolve ut with anything, convolution of ut by xt plus the integral. Yeah. Integral in S domain is 1 over the initial and final value. The initial value in time domain is related to the final value in S domain and vice versa. If you want x at 0, you need to find s xs when s is approaching to infinity. And when you want the steady state of xt, you need to find s x s when s is approaching to 0. If we do conjugation in time domain, we need to conjugate both s and its Laplace transform. And the system has inverse. The relationship between its the impulse response of or transfer function of its inverse with the original system should be 1 over h. Any question up now? Let's do something. From circuit theory, you became familiar with these two elements. Here. This is capacitor, this is inductor. What will happen if I move capacitors and inductor to S domain? I know the relationship between the current and voltage of capacitor. If I move it to Laplace or S domain, IC would be yes, which means Vs over we call it as the impedance. Yes. For inductor, I1. It would be LS. If we want to move these values to phasor domain, we just need to replace S with J. Okay. Okay, now design a system. Find the transfer function of this system. If I want to have tau equal to 4 seconds. And please do this assignment, and I'm gonna check the answer with path view. You are designing a system. Yeah, you will give me one transfer function. I'm gonna put it in the path view and see you did really good job or not. You are designing a control system, which is the answer would be something like that. This would be 4 tau, which means 16 seconds. Okay, I'm waiting for your answer. What is the current is function that it has only R, B, and how to be over time. So when you were writing professor, you remember the over time. Right now, you're telling me what over time. That's true. After, oh, output is capacitor voltage. It should be like you found it 4 over s plus 4, 1 over 4s plus 1. Yeah, here is like, oh, how come? Oh, so almost in 16 seconds, it reaches to 98% of its final. No, it started from 1. It should be 70. Yeah, in 17 is 98% of its final value. Now we want to make it a bit harder. If I add one inductor here, what will happen? It would be the second. Can you find the transfer function? Suppose L is 1, C is 1, and R is 1. Right now, I'm changing the output from capacitor output to inductor current. Now, your transfer function should be ILS over V. This is second order transfer function. We want to see what is gonna happen in the time domain. Now we are modeling our circuit as a transfer function, yeah, as a control system. All one, R, C, and L. Another practice if you are gonna have a circuit exam next week. Oh, yeah. Me killing the Anyone found? What it should be second order. Check something should be okay. Yes. No, no, no. No. Yeah, it should be second. I made a mistake here. That's why let me do it again. No, should be second order. It's it's Vs over 1 plus one. Yeah, that one. Value. Now find the answer for the input of unit step. If I apply unit step, what should I see at the output?
We have this to multiply by 1 over. Yeah. Multiply by
You need to find in a time. Yes. Yes. You know, if I apply UT, how would be the output in time domain? Right now, we consider this as a system. Vs is input, IL is output. If you consider Vs as a UT, its Laplace transform is 1 over x. How would be the output IM? For S, you know how to take the other how to use number. Right now, up to here, we are for this one. We should change it. Yeah, we should. Right. Yeah. 1, 1, 1. I think you can simplify it like this one. Okay. What is the Laplace transform of 1 over S ut? Yeah. How about the second one? What is the Laplace inverse of the second term? At first, we can consider it like S over S2 plus 3 over 4. Yeah. We can, I write here, S2 plus 3 over 4. What is Laplace inverse of this one? This one. It has S in numerator. It should be cosine. Yeah, yeah. Cosine of what? Yeah, root of 3 over 2. But this one, the difference is I changed t to t plus 1/2. When I changed s to s plus 1/2, which means shift in s domain. So in time domain, I should, yeah, exactly. It should be e to power of minus t, that's the coefficient, e to power of 1/2t. Yeah, if you remember, e to power of at0 xt e to power of at xt, it should be x minus a. How about the last one? I don't have space here. Let me delete this one I write here. How about this one? Again, it's 1/2 over f2 plus 3/4. That's sine. Yeah. But sine of at, what was the, let me write. What was the Laplace transform of sine of at? It's a. And now we have f2 plus 3/4. Here I should have root of 3/2. Yeah, but here I only have 1/2, which means I should multiply it by 1/√3. And now these two are the same. So this would be 1/√3 sine of √3/2t. So after that, I need to change f to f plus 1/2, which means I should multiply this by 1. So these are, and plus this. This is the result. Do you remember from circuit theory what kind of damping is this? Let me write it clean here. Answer it. What kind of damping is this? The circuit is overdamped, critically damped, or underdamped? That's underdamped, yeah. If you remember, it would be something like that. If we write this transfer function in the path view. I just need to set all the coefficients to 1 here. The denominator is s2 plus 1, s2 plus s plus 1, and numerator is only 1. And you can see if we apply one step, if I change it to if we want to change the frequency. I want to change the frequency to see it more clearly. See that on the so as you saw, it doesn't matter what kind of system we are dealing with. We can model every system which is defining by differential equation as a we can find the transfer function, and you will see in the next chapter how we can control some parameters of different systems. As you saw, if we can write one system with differential equation, we can easily move them, the equation, to the S domain. We can find the transfer function. After that, we can find the output in S domain, and we need to apply Laplace inverse to find the output. If a system is causal, do you remember if a system was causal, its HT would be 0 for negative time. So which means HT should start from 1 point and it's right-sided, yes. If HT is right-sided, so its ROT should be again right-sided. So a system is causal if its impulse response is right-sided, which means its ROC should be again right-sided. A system is stable if it has Fourier transform. We saw in a conditions of Fourier transform, a system is stable if it has Fourier transform. And where is Fourier transform? How we can find the system has Fourier transform or not? If we put sigma 0, which means if the imaginary axis is in the ROC. If ROC includes the imaginary axis, J omega axis, we can say the system is stable. For example, that is the first order circuit. First order system. They ask us to find the transfer function and impulse response of this system if that's causal. At first, we should move it to S domain. We know if we do derivation or differentiation in time domain, in S domain, we need to multiply it by S. Coefficients are the same, and Laplace transform of X gives XF. If I take a factor of YF, it would be S plus 3, and transfer function would be something like that. Since they ask us if The system is causal, which means ROC should be right-sided. So it has one pole, which means if there is one pole on -3, that means ROC can be only this side or this side. We know ROC cannot include any pole. So since they mentioned it should be causal system, we should consider the right side. Why it's important? If they didn't mention that causal, what would happen? If I don't know ROC is the right side or left side? Because this one I can write the answer e to power of -3 ut or minus e to power of -3 u minus. Okay. This Laplace transform has two inverse. Which one should I choose? Based on ROC. So if ROC now is causal, which is right-sided, the answer is this one. If two systems are parallel, we just need to add the transfer functions. If they are in series, as we know, we need to multiply the transfer function. How about the feedback system? If we have a feedback, we will talk a lot about feedback in next chapter, but just for practice, how do you find the Laplace transform of transfer function of this system? I can write here in S domain xs, here x1 s. That's ys, and again this one is ys. Okay. Y2s regarding to ys. Y2s is ys multiplied by h2s. Okay. Input multiplied by transfer function is the output. How about x1s? It's exactly xs minus y2s. Y2s is xs minus ys h2. Now, from this system, ys and xys, ys is h1s x1, which is h1s xs. So ys is h1s xs minus h1 h2s ys. So I will have ys is if I move this part to the left side, I will have ys1 plus h1. So hs is ys over xs, which is h1 is 1 plus h1 is h2. Yes, this is the transfer function of the system with feedback. You will see in next chapter how this can help us in too many different aspects. You know, the H1s is transfer function of this system. H2s transfer function of, we call it feedback system. Okay, here are some important Laplace transforms. I think you now know almost all. UTN minus U minus T, both same 1 over S. The difference is between these two. What is the difference? ROC, exactly. For the, what is ROC of this one? Right side, which means from where to where? From 0 to infinity, because the pole is in 0. How about this one? ROC? Yes. From minus A to infinity. This one, minus infinity to minus A. This one, the whole is plane, except infinity. Yeah. If S can be minus infinity, yeah, its really part can be minus infinity, so in infinity. How about this one? Bounded by no. At first, the signal in time domain is right-sided or left-sided. So if signal in time domain is right-sided, its Laplace transform should be right-sided. From where to where? 0 to infinity. The root is j omega. Yeah, the root is, which means the 0 to infinity. Same for the other one. And this one just shifted to minus alpha to infinity. Okay. Now I want to finish. We have 5 more slides, and I want to finish this topic today. Please let me go ahead. It's only 5 or 10 minutes, not more. I know you are a bit tired. I can see from your eyes, but just let me go for 5 or 10 minutes. Have you heard about sampling? Why do we do sampling? What sampling means? In fact, when we are dealing with the outside world, everything is continuous time or analog. Yeah, but we need to do our processes and calculations in digital domain or discrete time. Anyone knows why? So why didn't make the computers analog? Why computers are working with digital or discrete time signals? It has too many benefits. The simple one, it consumes less power. They are more immune to noise. You know, when you have an analog signal, if one small noise affecting that, your signal is changing. But in digital, you have 0 and 1. You can put a threshold. For example, if you consider the voltage less than 1, you can consider it as a 0, more than 4 volts as a 1, which means you have a big margin for noise. And we can integrate digital systems. It's more immune to noise. It's cheaper and too many advantages. That's why we want to move the signals from analog domain or from continuous time to discrete time. But for doing that, we usually do sampling. What is sampling? Suppose we have xt, one signal which its Fourier transform is something like that. It's limited in frequency. It has like our voice. Yeah, we can generate not more than 3 kilohertz. Yeah. In frequency, we don't have parts of frequency more than 3 or 4 kilohertz. So if we multiply xt by train of impulses, these are train of impulses. If we multiply xt with this train, what will happen? Suppose at first it's only 1. If you multiply xt by delta t, yeah, which means we are taking one sample from delta. It should be x0 delta. Do you remember what will happen in frequency domain if we do multiplication in time domain? Multiplication in time domain is equal to convolution in time domain, yeah? That's vice versa. If we do convolution in time domain, that's equal to multiplication in frequency domain. If we do multiplication in time domain, that's, multiplication in time domain is convolution in frequency domain and vice versa. Now I have multiplication in time domain. It should be convolution in frequency domain. Convolution of everything with delta with everything. So this is xj. Now if I have xt and I multiply it by delta t minus t0, it should be convolution of x with delta omega minus yes. Let me know. This one I shouldn't say because we want a periodic signal. For one, we know it's gonna be this one. If I have periodic signal like that, if I have train of impulses, if you remember, its Fourier transform would be again one train of impulses in frequency domain. Now, if I convolve x with any of these ones, if I convolve x with this one, it would be x. If I convolve x with this one, it would be shifted to omega s. If I convolve x with this one, it should be moved to 2 omega s. And depending on if omega s is bigger than 2 omega n. Omega n is the maximum frequency that exists in the input signal. In that case, the output would be, you can see, we can easily see separate periodic of input signal. But if sampling ratio is less than 2 times of the higher part frequency of the input signal, we cannot, it's mixed. Yeah, we cannot recognize the input signal. Yeah. They have interfered together. So Nyquist rate is saying if we want to be able to reconstruct the original signal, we should do sampling rate with 2 times more than the higher frequency component of the input signal. Here is the higher frequency component of the signal. For example, when I'm talking that it's not more than 4 kilohertz. If you want to be able to reconstruct it, you should sample it with more than 8 kilohertz. Yeah, exactly. How do we reconstruct? Again, we multiply it with a train of impulses. And at the end, if we multiply this, it would be something like this. And if we apply when low pass filter, something like that, you saw low pass, how we make low pass filters, yeah? The easiest way was RC circuit, yeah? Right now, you find, yeah. If S you, this is H. If S is small, it would be 1. When S increasing or J omega is increasing, it's gonna drop. Yeah, that's one low pass filter, but this one is ideal low pass filter. That's really sharp. Which means if we have one low pass filter like this here, we can just filter the signal and omit the other one. So we can reconstruct the original signal. So, okay, this is easier. We find this earlier. We know this, we find them earlier. These are really easy for us. How about this one? The transfer function, we move all to the S domain. If system is causal, which means ROC should be right-sided. So we can easily find. If system is stable, which means ROC should be yeah, it should be. But we suppose system has Laplace transform. If system has Laplace transform, and if we call it stable, which means the J omega axis should be inside the ROC. Yeah, we talked about. You are right. If system, the port should be in left side. If system wants to be stable, yeah. And non-causal and unstable, none of the above conditions. Yeah, you can see these by yourself. And I just want to show the last one. How about this one? What is the final value of causal system with impulse response of this? Yeah, but we had one relationship, yeah. The final value in time domain is if I multiply S by its Laplace transform and find it at S0. We can use this one. It would, yes. But is it true? That's just my question. Okay, for next session, that's your exercise. Just investigate this answer is true or not. For next session. Investigate this answer which I wrote here is true or not. If it was true, why should I ask you? That, you know, I used that formula which we had. Yeah, we had in properties of Laplace transform. Yeah, to find the final, to find the steady state of Y. Yeah. And the answer is minus P/2. Do you think this answer is true if I make this system in real and if I apply 3ut, when t goes to infinity, it would be something minus 3/2. The answer is here. Find the Laplace inverse. Okay. Next session, we will see who is able to find the problem. Okay. Any question? We just finished the Laplace transform. For next session, we will go through control system and we see some timing responses. After that, we go through stability analysis in S domain and not more than 2 or 3 sessions. And finally, we will go through our job, which is electronics. And these are the things you need to know before starting the designing electronic circuit. Yes. After 3 or probably 3 sessions, we will go through a bit physics of components, and after that, we will go inside the circuit, and we are gonna learn how to design ICs. Any questions? Thank you. See you tomorrow. But for the, I just made a poll for, because some of your friends were asking me to change the time of the class to afternoon. I put a poll, but the answer is not clear. Yeah, we don't know we should continue this time or we should move to afternoon. I think your friends are playing with us. Yeah. Because that, okay, let's find out how we can sort this out.
It will be better with the break.
Yeah, but what you see, yeah,
Morning session.
morning session 15 people and Afternoon only. I know they are not joining, they are just playing. They try to make them balance. Okay, thank you very much. You tomorrow. Tomorrow again we will be on 10 to 12. It is, but we should satisfy the maximum of the training. Yeah, but I made a poll right now.
Because if we try to consider the ones who have the summer semester, it's better time.
If we can try afternoon, can you think we can try afternoon to see? For all you, is it possible to come afternoon? You cannot? No.
One day afternoon better or just one day afternoon?
Okay. Let's try one afternoon and to see maybe more people can join. Okay, thank you very much for your coming. If you had any questions, feel free to take you.
Yeah, I think we cannot use this.